So good morning, everyone, or good afternoon, depending in which part of the world you are. Welcome to this masterclass. This is organized in conjunction with the Arua de Guild Cluster of Research Excellence in AI, and it is intended as a first appetizer into quantum computing. Yeah, the motivation being that this is the International Year of Quantum Science and technology that was launched just a month ago in Paris at UNESCO. Yeah, so the idea of this talk is to give you a very brief introduction to the and maybe in several weeks, a couple of months, maybe we will follow up with another masterclass where we will introduce more advanced concept until we reach then maybe the introduction to some serious quantum algorithms and things that you can do on a quantum computer that you can have access to in the cloud at the moment. Yeah, so we will start with a little introduction, a little historical and background. Yeah. Then we will introduce the concept of the qubit as the basic element of quantum information. Yeah, we will play a little bit with a single qubit. We will look at some one qubit algorithms. Then I will bring to an end this part of the talk. And in the last half an hour, my famous PhD student, Dean Brandt, will show you how to transform all of that I'm telling you now into Python code. Yeah. So the idea is to spend an hour and a half maximum together this morning. Yeah. So let's start with the introduction. Yeah. As I mentioned, 2025 is the International Year of Quantum Science and Technology. Yeah. And the idea is to and it's been supported by many countries. And the idea is to promote all aspects of quantum science and technology. It is in the year 2025 because one can date the birth of modern quantum mechanics almost exactly 100 years ago. Yeah, and the idea is that to promote across all areas of theory and application the ideas and concept of anything quantum. Yeah, we are supposed to celebrate the progress in quantum mechanics and quantum technology. Yeah, for all branches of our life, from health and well-being to renewable energies and so on and so forth. Yeah, so this is the aim of the celebration of quantum physics in this year. Yeah. So why do we want to focus on one single qubit in this lecture? Yeah. This is mainly for the three reasons that you see up here. Yeah, mainly for the simplicity of the qubit concept. You know, quantum mechanics is foreign to many people that are not physicists. Yeah, and we want really to find a way to invite as many people as possible to appreciate the elegance of quantum computing. Yeah. At the same time, it's the fundamental element of quantum information, and without understanding the qubit, all the more advanced concepts won't be easy understandable as well. Yeah, and finally, there are already really practical applications that we can achieve with a single qubit. Yeah, and some of them we will discuss as we move on. So let's start with some historical background. Yeah, more than 100 years ago, classical physics started to show some. It was Max Planck, exactly in the 1900s, that came up with a radical postulate to say that energy is emitted and absorbed in discrete quanta. Yeah? And he formulated the famous equation that E is equal to h times nu. Nu is the frequency, and h is a very small number, as you can see, which bears now the name of Planck. Yeah, and a few years later, he was awarded the Nobel Prize for this important discovery. But it was at that stage just a trick to patch some of the observations that didn't match the current theory. Yeah? It became way more physical a few years later when Einstein used the concept of the Planck constant to explain the photoelectric effect. Yeah? And this was also the reason for him to get the Nobel Prize 15 or 16 years 15 or 16 years later. I won't go now into the details of all of this. Yeah, but this was the famous paper in which it was assumed light is quantized in discrete photons with a finite energy. Yeah, a few years later, Bohr, it was Bohr's term to win the Nobel Prize. Yeah. And Bohr came up with a famous quantization condition, yeah, because the classical model of the atom in which electrons were just orbiting around the nucleus had a very big weakness that, according to the theory, the electrons through their motion radiate energy and should have fallen into the nucleus, which was not what happens in practice. Yeah? So, and Bohr came up with a very important idea that the angular momentum of the electrons moving around the nucleus should be quantized. Yeah? And again, you see that the condition for the angular momentum is again that includes again the Planck constant. Yeah? This time h bar is just the Planck constant divided by 2 pi. Yeah? So in this trick, yeah, he was able to explain the hydrogen spectrum. Yeah? And that, again, a few years later, earned him the Nobel Prize. Yeah? Things got a little bit more interesting around that time as well, when de Broglie realized that that not only light has the property of being sometimes a wave and sometimes a particle, but matter itself. Yeah. And you see here the famous equation relating the wavelength of matter to the momentum of matter. Yeah? And this also earned him the Nobel Prize fairly quickly, because just a few years later, experiment confirmed his theory. Yeah? And now we are at 1925, which is the birthday that we're celebrating this year. Yeah. And this was the famous matrix mechanics of Werner Heisenberg. Yeah. And this is essentially the beginning of modern quantum mechanics. Yeah, I won't go into the detail equation of motion. Yeah, but it was the beginning of thinking that electrons don't really move on orbits. Yeah, that something else is going on. Yeah, and those are the things that we are exploiting now in quantum computing. Yeah. Soon after Heisenberg, Schrödinger came up with his famous Schrödinger equation that we will make use of just now. Yeah, and as you can see, he was not a big fan of the Heisenberg approach. Yeah. And this is probably the most popular approach now that we have to quantum mechanics. Born was then able essentially, and others, to show the equivalence of the Heisenberg and the Schrödinger approaches, and he's responsible for the statistical interpretation that most of us use up to this date of quantum mechanics, and that brings establish a relationship between the square of the wave function in the Schrödinger equation with the probabilities of what is observed. And it turns out that, as I mentioned, that the wave and matrix mechanics are equivalent, and we will make use of it all the time. Yeah. So the reason why this is all exciting is that, you know, quantum mechanics was born, let's say, 100 years ago. But the real impact of quantum mechanics, besides explaining some of the standard observation, was the technological application. They are like transistors, laser diodes, famous CPUs, medical applications like MRI. And it took a long while for those to materialize. So that we could, in principle, say that the first quantum revolution gave rise to the third industrial revolution. Yeah? and these days, people claim we are at the beginning of a second quantum revolution that hopefully will give rise to another industrial revolution. So the second quantum revolution started in the 80s, yeah, when people like Hans Demel, for the first time, were able to observe single quantum particles. Yeah, in the case of Demel, it was just ions in an ion trap, and that also led to Nobel Prizes very quickly. Yeah, so this is the qualitative jump that happened in the 80s. Yeah? The fathers of quantum mechanics never had the opportunity to see. Yeah, they never observed a single quantum system. Yeah? It was always quantum systems in the bulk or ensemble properties, yeah? But never single quantum particles. Yeah? What Demel did with atoms, with ions, other people like Harosh and Weiland did also with single atoms and photons, and they also showed us how to control these individual quantum systems, and that also led to Nobel Prizes. Yeah? And this is what we are using in these new quantum technologies that are emerging. Yeah? I won't speak today about entanglement, yeah, but this is the last piece in the puzzle that we need to exploit the full potential of quantum technology, and this was awarded a few years ago to Elena Specht, John Clauser, and Anton Zeilinger, yeah? For the experimental realization of what John Bell pioneered in the early 60s. So, summing this all up, seen at the end of the last century, the merger of quantum mechanics and information science. Some people call it quantum information science, and the idea is that information can now be stored, processed, communicated exclusively according to the laws of quantum physics. Yeah? And the three major technologies that are emerging are quantum computing, quantum communication, and quantum metrology or quantum sensing, yeah? Which might form or will form the pillars of a future quantum internet. So now this was the sort of historical introduction. Yeah, let's move on to try to understand the qubit. Yeah, how do we go from the classical bit to the qubit? Yeah, the classical bit, as you know, is just 0 and 1. Yeah. The qubit is a different object. Yeah? A very primitive quantization procedure would be just to replace the bit 0 by a two-dimensional vector 1, 0, and the bit 1 by a two-dimensional vector 0, 1. Yeah? And to keep the notation similar, we call the vector 1, 0 the cat 0, yeah? in this so-called bracket notation, which is due to Dirac. And the vector 0, 1, we just call it the cat 1. Yeah. So one of the famous properties of quantum mechanics is the superposition principle, so that the general state of a qubit can be a superposition of the cat state 0 and the cat state 1. Yeah, where alpha and beta are complex numbers normalized to 1. So this is the general state of a qubit. Yeah. How can we visualize the qubit? Yeah, there's a very simple visualization procedure. Yeah. Whereas the bit can be visualized as a switch that allows current to flow or not to flow. Yeah. The qubit can be visualized as a vector that goes from the middle center of a sphere to the surface of a sphere. Yeah, with 0 at the north pole and 1 at the south pole. Yeah, and every point on the surface of the sphere, which is made obvious by the parameterization that you see here at the bottom. Sorry, I don't know why my pointer doesn't work. Anyway, yeah, is a legal qubit state. So you see immediately visually that the qubit and the bit are two completely different animals. Yeah? So let's let's do a little bit of quantum mechanics and introduce the postulates of quantum mechanics just for the qubit. Yeah. The first postulate of quantum mechanics is the so-called state postulate. Yeah. And it says that a qubit is represented by a normalized state in a two-dimensional complex Hilbert space, like we saw in the slide before. Yeah, like those vectors that point from the middle of a sphere to the surface of the sphere. Yeah, and the general qubit is a superposition of 0 and 1. Yeah, with alpha squared plus beta squared equal to 1. Yeah. One of the not so intuitive aspects of quantum mechanics is the measurement postulates that states that when you observe a quantum state, yeah, after the measurement, the state collapses in one of the eigenstate of the observable. So it means that, for instance, in the case of our qubit here on Hilbert space, after the measurement, the state will be either 0 or 1. Yeah. And 0, 1 appears with a certain probability. Yeah. Alpha squared for 0 and beta squared for 1. Yeah. So this is the so-called measurement postulate. We still need something for the dynamics of the qubit, and the dynamics of the qubit is essentially given by the Schrödinger equation. Yeah. So the fundamental aspect is that just by simply integrating the Schrödinger equation, one can see that the evolution of psi from psi 0 to psi t is given by a unitary operator, which, if the Hamiltonian is constant in time, has the very simple exponential form, which explains why it is unitary. Here, I just wanted to rephrase the previous slide with explicit connection to the Schrödinger equation. Yeah. So the unitary dynamics that I've shown on the previous slide is just a formal solution of the Schrödinger equation. And psi, in our case, is just a two-dimensional complex vector representing the general state of a qubit. So one fundamental property of the Schrödinger equation that is important for the following, yeah, is that we want, you know, what we measure to be real, yeah, because what we measure we can touch, and we want it to be real and not imaginary. Yeah. So, for instance, in the case of energy, yeah, if the Hamiltonian represent the observable of the energy of the system, and if we look at the time-independent Schrödinger equation for simplicity, we want the energy E to be real. Yeah. So, and this is imposes a condition on a Hamiltonian to make it Hermitian. So we want H to be H, the Hermitian of the to be H deca. Yeah. For a very simple qubit, yeah, the Hamiltonian can be written as a 2 times 2 matrix. Yeah. And if you want it to be Hermitian, it must have the structure that you see here on the right-hand side. And if you do a little bit of maths and you diagonal this, you will see very quickly that the eigenvalues of this Hamiltonian are real. Yeah. So this is something very important to keep in mind. Yeah, let's do this explicitly for the qubit. Yeah, let's assume that we have a very simple Hamiltonian. Yeah, sigma, some constants. Yeah, the energy times sigma z. We will introduce it just now as very special matrix that has this form 1, 0, 0 minus 1. Yeah, this is one of the Pauli matrices that I will introduce just now. Yeah, we can now solve explicitly, very simply, the eigenvalue equation, assuming that the qubit has components A and B. You can set up the eigenvalue equation and do a little bit of math, and you will see that the eigenvalues in this case are plus and minus h bar omega over 2. Yeah, and they're obviously real. They're not positive. One of them is negative, but they're obviously real. Yeah. So this is just a very simple example. Yeah. Now, we have this very nice picture of the qubit on the Bloch sphere. Yeah. And it's very useful to keep this picture in mind and generalize it to the dynamics. Yeah. Let's look again at the same Hamiltonian that we had before. Yeah. H is a very simple proportional to the simple matrix 1, 0, 0, -1 that we have before. Yeah. The time evolution can also be very easily expressed, yeah, because everything is diagonal. So you find the unitary operator T is just exponential of e to the minus I T half omega times sigma z. If we use now the fact that sigma z is equal to 1, and we expand the exponential, yeah, I don't do the maths, but I assume that you can do it. Yeah. Then you can see that u von t can be written as a simple rotation, yeah, around the axis z on the Bloch sphere. Yeah, so unitary rotations are also some kind of rotation of the qubit on the Bloch sphere. Yeah, you can also do it more generally. Yeah, in general, you can decompose an arbitrary Hamiltonian in terms of the three below, which are the famous Pauli matrices, yeah, sigma x, sigma y, and sigma z, plus the identity. Yeah, for the purpose of the dynamics, the identity is not so important because it just adds a phase that is not so important. Yeah, but what is now nice is that for this most general Hamiltonian of a qubit, yeah, you can do the same game. Yeah, you can calculate explicitly the unitary operator u of t again by exponentiation, expansion, and so on and so forth. And you can show explicitly that in the general case, the unitary evolution of the qubit is just given by a rotation around an arbitrary axis of the Bloch sphere, yeah, for a specific angle, capital omega, yeah. So this is a very nice picture to keep in mind, yeah. So now we need to slowly get a connection to the language of quantum computing. Yes, this was, so far it was just the standard language of quantum mechanics for a two-dimensional state vector. Yeah, I introduced the Pauli matrices as a basis of matrices in a two-dimensional, 2 times 2-dimensional complex Hilbert vector space. Yeah. And we've seen that we can easily introduce rotations around the various x, y, and z axes as, let's call them r theta, yeah, e to the minus e theta half sigma x, y, or z. Yeah. Now, for very specific rotations, for instance, around pi, yeah, Rx of pi reduces essentially to sigma x, yeah, up to a factor minus I that is not so relevant, yeah. And in quantum computing, people use the gate x, yeah, which is essentially sigma x up to the factor e to the minus I, yeah, which for all practical purposes is just a global phase and doesn't play any role. Yeah? So we have, as a special rotation around x for the angle pi, we can introduce the operator x, yeah, which will be the famous x gate of quantum computing. Yeah? If we do the same angle rotation in y and z, yeah, you can do the same math, yeah, and you can show that ry around the angle pi is just sigma y, and you eliminate the global phase, and that's defined as the operator, as the gate y, yeah, and the same you can do with z. Yeah? So this is how the x, y, and z gates came about. Yeah, they're just operators that describe the unitary evolution of a single qubit, yeah, in x, y, and z. Yeah, and if we sorry, sorry, I thought I had a nice summary where I show you how they operate, but it's the next slide. Yeah. You can also introduce other gates. Yeah, a very famous gate is the Hadamard gate. Yeah, the Hadamard gate is defined is 1 over square root of 2. This matrix 1, 1, 1 minus 1. And if you look at the decomposition on the bottom of the slide, you see it's a combination of rotation around z and around y. Yeah, so it's also built by elementary rotation. But what this particular gate does, if you look at how it operates, for instance, on the state 0, yeah, it creates a superposition of 0 and 1. Just you multiply 1, 1, 1 minus 1 with 0, 1, and 1, 0. Yeah, it's not very difficult math. Yeah, and if you apply it on the state 1, it's again a superposition, but with a minus sign instead of the plus sign. Yeah. So if we sum up everything, yeah, we've seen now the X, Y, Z, and the Hadamard gate. Yeah, the X gate is sometimes also called the NOT gate. Yeah, because if you look how the matrix 0, 1, 1, 0 of the X gate operate on 0 and 1 and 1 and on 0 and on 1, it just does the bit flip. Yeah, 0 becomes 1 and 1 becomes 0. Yeah, the Y gate is a kind of a bit flip complex conjugate. Yeah. Yeah, it does 0 goes into 1, 1 goes into 0, and there is an I in between. Yeah. The Z gate is the so-called phase flip, yeah, because it keeps 0, it maps 0 to 0, but 1 into minus 1, yeah. And Hadamard creates the superposition. Yeah. So these are the four most fundamental, and the identity, of course. Yeah, these are the four most fundamental gates for a single qubit, on how you can manipulate a single qubit. Yeah, and of course you have all the rotation gates as well, like that we introduced before. Yeah, but these are the probably the most famous gates of quantum computing for single. Now we have a qubit. Now we know how to manipulate them. We saw the postulates for a single qubit. Yeah. Now we want to play a little bit with qubits. Yeah. And I just want to again show you some of the fundamental properties of quantum mechanics in the language of the qubit. Yeah. One very fundamental aspects of quantum mechanics are rapid oscillation. Yeah? This is just an expression of the coherent quantum dynamics. Yeah? So for instance, if you look at a very simple Hamiltonian, yeah, you couple a qubit to an external electromagnetic field. Yeah, the qubit has Hamiltonian sigma z. The electromagnetic field is described by sigma x. Yeah. Technically, omega, capital omega is the so-called Rabi frequency, which is somewhat proportional to the amplitude of the driving. Yeah. And if you look at it at resonance, but delta is 0, yeah, you just have sigma z, you can simply integrate the equation of motion, and these famous Rabi oscillations appear. So you can see really that the oscillation keeps going forever. Yeah. And what we have plotted here is the probability to observe one at a certain time. So the system can oscillate between 0 and 1 forever. Yeah. Yeah, so this is a standard example of a coherent behavior, dynamical behavior of a qubit. Yeah? This is what you want to have in quantum. Of course, if you build a quantum computer, there will be noise effects, so it will dissipate away. Yeah, but that's a discussion for another masterclass. Yeah? As a first really basic application of a qubit, yeah, is the concept of a very simple quantum random number generator. Yeah, you all know generate random numbers is typically a mathematical procedure. You have an algorithm that produces numbers that are almost random. Yeah, but with qubits, you have really the opportunity to realize random numbers that are truly random, yeah, because of a physical procedure. Yeah? And you can buy such random number generators. Yeah? There are even Samsung phones that have such a random number generators built in for security purposes, because you need random numbers to generate secret keys and things like that. Yeah? So people already use it. Yeah. And the idea is just to put what I'm telling you now on a chip. Yeah, that's all. Yeah. So how can you do a random number generator? Very simple. For instance, you generate, and this is our first encounter with a quantum circuit. Yeah. We have an initial state on the left, the state 0. We have a Hadamard gate, and we measure. Yeah. So the dynamics is from left to right. Yeah. In the circuit. If you write the equation, it's just the other way around. Yeah. So what does the Hadamard do on the state 0? It creates the superposition. So the psi that we are going to measure is just 1 over square root of 0 plus 1. Yeah. When we measure this, what happens according to the postulate that we discussed before. With probability 1/2, we measure 0. With probability 1/2, we measure 1. Yeah, and that's your random. That's your random number generator. You just need to repeat it many times, and you generate perfect random numbers. Yeah, and this you can do these days easy on a chip. You can do it with photons and many other technologies. Yeah, so that is this is just one. On paper, very simple. To build it, it might be more complicated, but on paper, it's very simple. Yeah? Another very simple example where you can see the interference effects of quantum mechanics in action. Yeah, is the quantum circuit formulation of the famous Mach-Zehnder interferometer. Yeah, where you have a qubit entering a Hadamard in a quantum optical setup. The Hadamard would just be a beam splitter. Yeah, then you have a little bit of a phase shift, another beam splitter, and then you measure. Yeah, that would be the setup. In quantum optics, has 2 beam splitters and 2 mirrors. Yeah, if you translate it into the language of qubit, you have your photon. Yeah, in state 0. Enters the beam splitter, which is Hadamard, yeah, enters the phase shifter, which is essentially a rotation around Z with an angle phi, yeah. Enters the next Hadamard, which is the next beam splitter, yeah, and then you measure, yeah. And now if you can do all the maths, yeah. If you start in 0, after Hadamard, you have a superposition of 1 and 1, yeah. After the phase shift, the 1 becomes 1 e to the I phi. Yeah. Then you have another Hadamard, which creates another superposition of 1 plus e to the I phi, 1 minus e to the I phi with the corresponding normalization factor. And when you measure, yeah, the probability of measuring 0 is the cosine square of the phase shift, and the probability of measuring 1 is the sine square of the phase shift. Yeah, and this is a typical interference pattern that depends on the shift in phase that you apply. Yeah, if there is no phase shift, you always measure the same. Yeah, the phase shift, the famous interference pattern emerge. Yeah? And this is just standard quantum optics now re-expressed in the language of qubit dynamics and quantum computing. Yeah. Okay, so this was just some very simple quantum mechanical aspects known for 100 years, re-expressed in the language of qubit dynamics. Yeah? Now, let's move on to some simple quantum algorithms, and this is where you need to pay attention, because then Dean will show you how to program them. Yeah? So let's start with one of the first practical application of quantum technology, yeah, and this is the famous BB84 protocol for quantum key distribution. Yeah, so the problem is you want to generate a secret key using quantum physics. Yeah, this is just a cartoon. Yeah, the cartoon is you use single photons. Yeah. Alice sends a 1, yeah. So Alice needs to send a basis, choose a basis for the polarization of her single photon. Yeah, this is just kind of a vertical polarization. And let's say that 1 is vertical polarized photon. Yeah, of course it goes through her filter. Bob on the other side also in this example chose the right basis for his measurement, so he measures exactly the same. So if Alice sends a 1, Bob has chosen the right, and he measures 1 with 100% probability. Yeah? But in order to set up a communication protocol to create a secret key, yeah, Alice doesn't tell Bob what basis he has chosen. Yeah, so Alice sends again 1. Yeah, Bob doesn't know, so he chooses now an X kind of 45-degree turned basis. Yeah. So what happens then? Yeah, according to the rules of quantum mechanics, Bob has then a 50-50 chance to measure 0, 1 in his new basis. Yeah. So in this case, maybe he measures 0 with 50% probability. Yeah. Now, in the protocol, yeah, after this has been done many times, yeah, and they keep a record of what they have measured, what Alice have sent, what Bob has measured. Yeah, they pick up the phone, and Alice tells Bob what basis she has chosen. Yeah, and then Bob knows which are the right qubit and which are the wrong ones. Yeah, the beauty of this algorithm is that if an eavesdropper intervenes, yeah, picks up the photon of L that Alice has sent, yeah, and measures it, yeah, the eavesdropper needs to send it back to Bob, yeah, and that changes the statistics of what Bob measures, yeah. So by looking at the statistic of what Bob measures, they know whether someone interfered or not, yeah. And this is the basis of quantum key distribution, yeah. And the beauty of quantum key distribution, sorry, now they start they start drilling next door, yeah, is that it's a security, it's a secure way of creating a secret key based on physical principles, not on complexity like in most cryptographic tools. Yeah. So in the language of the qubit, yeah, we have these two steps, the preparation. Yeah, Alice chooses one of either a Z basis or an X basis. Yeah, if it is the Z basis, she just uses the qubit 0 and 1. If it is the X basis, she needs to rotate, and she applies a Hadamard before she sends it to Bob. Yeah. Then Bob again chooses to measure either in Z of X. Yeah. If they choose the same, they know that the bit is okay. If you choose another basis, they know that the outcome is random. Yeah. So that this is then the kind of the circuit representation of the BB84 protocol. Yeah. If Alice chooses the Z basis, then she just has the identity and measure. If Alice uses the X basis, she needs to send her photon through a Hadamard before Bob reaches it and chooses what she has. Yeah. And after this is done many times, there is the post-processing procedure that I mentioned before. Yeah. And other things. So this is the basic idea of a very simple but super effective protocol keys. Yeah. And people can do it in free space. People can do it in fiber optics. People can do it via satellite. Yeah. So it's something that has a really technological application and is the best security for a secure key that money can buy. Yeah, because it's physical security, is not mathematical complexity security that with a lot of computing power you could hack. Yeah. Okay. Now, this was just one aside on quantum communication because it's a historically important application of quantum technology. Now I want to introduce two classes of quantum algorithms, yeah, at the level of a single qubit. Yeah, one is a class of algorithms that maybe in later master classes we will use in more advanced setup that use so-called oracles. Yeah, and an oracle is essentially a black box that computes something. Yeah. Without you knowing exactly what's going on in the black box. Yeah, and in classical computing, and as you will see, we will use it in quantum computing as well. Yeah. So the black box that we want to use to use now, yeah, is this unitary operation UF, yeah, that just maps a bit into a bit. Yeah, and we want to have a so-called phase oracle. Yeah, we want is if U operates on X and X is 0 or 1, we want the result to be -1 to the power of f of x, whatever f of x is. Yeah, and if f of x is 0, the phase does not change, and the f of x is 1, the phase changes by -1. Yeah, so this is the UF that we want to look at as an oracle. Yeah. And with this oracle, we can define a very famous algorithm. The traditional formulation is for 2 qubits, but you can formulate a version also for 1 qubit, which is the so-called Deutsch algorithm. Yeah? And the Deutsch algorithm is intended to show the potential advantage of quantum algorithm, yeah, because it allows you, for one qubit is not so evident, allows you to appreciate the importance of quantum computing. Yeah, the circuit is plotted here. Yeah, you have the qubit in state 0, followed by a Hadamard, followed by oracle, followed by Hadamard, and then measurement. Yeah. So the 3 steps are indicated here. Yeah. So you see after the Hadamard, the qubit in state 1 is in a superposition. After the oracle, we apply the UF that we've defined here. Yeah. And you can, with very simple math, show that this is either plus minus plus, and the state plus is 0 plus 1 over square root of 2, and the state minus is 0 plus 1 minus square root of 2. So you have the state plus if f of 0 is equal to f of 1, and you have minus if f of 0 is not equal to f of 1. Yeah. Then you can measure, and you obtain 0 if f of 0 is 1, and 1 if f of 0 is not equal to 1. Yeah. And what the algorithm does is, it's in principle, it shows you a global property of the function f. Yeah, because with one call of the oracle, you can decide whether f of 0 is equal to f to 1, or f of 0 is not equal to f to 1. Classically, you have to compute f of 0 and compute f of 1. Yeah, with the oracle and this kind of quantum setup, you can decide that with just one function call. Yeah. And this is, you know, for one qubit, it's not so phenomenal. Yeah, but it's a kind of a demonstration that you can, with one function call, decide about a global property of a function. Yeah, if you had a function with n bits, it's the same. You just need one function call, whereas to check whether 2 functions are the same classically, you need to check argument by argument. Yeah, and here you have the possibility to check a global properties with just one function call. Yeah. So these are class of algorithms, these oracle-based algorithms that play a big role in more advanced quantum algorithms with many more qubits. Yeah. So the next class of algorithms that I want to introduce now are variational quantum algorithms. Yeah. These are very important for the class of quantum computers that are sort of mainstream at the moment, yeah, which are called noisy intermediate state quantum computers that don't have error correction. So where the noise builds up, where the Rabi oscillations are not perfect. Yeah, in time, if you apply many gates, the coherence fills away. Yeah. So the idea is very simple. Yeah, is to do something in the typical physics variational way. You introduce variational parameters and you optimize something. Yeah. And optimize means you run the circuit with a parameter, you evaluate some cost function of sorts, you minimize it, evaluate another parameter, and you do it again, yeah, until it converges. Yeah. And what I want to show you now is a very simple example. Yeah. So we prepare the state in a qubit state that depends from some parameter theta. Yeah. As an example, we want to calculate the minimum of the energy. Yeah, so we calculate the expectation value of the Hamiltonian, and we want to minimize it. Yeah, so we need a minimization procedure to optimize the parameter theta so that we get the ground state at the end, the ground state of the Hamiltonian. Yeah. So the first step is we need to prepare the parameterized state. Yeah. That we can do with one of our famous rotations. Yeah. If we use Ry, for instance, and apply it to 0, we can create the standard superposition, the general superposition of a qubit state. Yeah, so that's a good way to start. Yeah? And for more complex algorithm later with many qubits, it's essentially the same. You will have lots of Rys acting on many qubits until you have inputted the data that you want. Yeah? So then, we chosen, for instance, in this example, yeah, a simple Hamiltonian, again, something diagonal. Yeah? The Hamiltonian is just the zk. Yeah? So it's easy then to calculate the expectation value of the energy. If you do it with psi of theta, it's just the cosine of theta. Yeah? So what the algorithm does, then you start with a psi of theta. You calculate E of theta. You minimize, you calculate, you try to minimize the cost function. Yeah, you have a new theta. You go back in, until you reach the minimum. Yeah, until you reach theta equal to pi. Yeah, when you have reached equal to pi, you know that the ground state is -1, and that your energy is also -1. Yeah, yeah. So that's the idea of the variational circuit. Yeah, you do this, you iterate this procedure, many times. Yeah. Okay, so I think I'm coming now to an end of my part, because I want Dean also to have half an hour to show you how to do all of this in Python, how to program it. Yeah. So what we've done so far is, you could say we just learned the alphabet of quantum computing. Yeah. The single qubits. Yeah. And we've seen superposition, measurement, and we played around with a little bit, yeah, and saw some basic classes of algorithm that you can then generalize to many qubits to solve many more problems. Yeah. So what we have not touched upon, yeah, is, for instance, the concept of entanglement. Yeah, the moment you have more than one qubit, yeah, there are more postulates of quantum mechanics that show you how to treat composite quantum mechanical systems. Yeah, and there things like entanglement come into play. Yeah, and that is another ingredient for many other algorithms. Yeah, that maybe we will do another time. I thought there was no point in rushing through everything. Yeah, let's maybe in a month or two we have another masterclass and we'll do a little bit more complicated things. Yeah, and now I will leave you to Dean. Yeah, and maybe while Dean shares his screen, if you have any questions, you're most than welcome to ask. And Donovan will have, there is a raised hand. No. No, they see a raised hand. Yeah, let's, here. Please, you're welcome to ask your question. Tebogo, can you hear me? Hello? And in Amantica, we also gave you the permission to talk.
Hi, hello.
Hello.
I am new to quantum computing, and I'm just observing it for the first time, and I'm trying to understand. Oracle seems like a gate, is it?
Sorry, say again.
I'm asking, is Oracle kind of a gate?
Yes. It's a unitary gate. Yeah, but you don't really know what's inside.
Okay. So basically, it's quantum mechanics and sort of principles of electronics. There are many gates like that, and then we are mixing it, and what we are getting is computation.
Yes. And when we have later on more than one qubit, there will be other classes of gates that combine more than one qubit, yeah, to achieve other things. Yeah.
Okay. Thank you. It was a very great introductory lecture.
Thank you very much. Glad you enjoyed it. And you were the target. We wanted to address people like you that had no idea of quantum computing. So
yeah, I had idea of quantum, but I did not had idea of computing. But
That's
realizing it's mixture of quantum mechanics and electronics.
Yes, if you want to look at it like that, that's exactly how it is. Yeah. Thank you.
Hi, Professor.
Hi.
I'm muted now. Thank you for the insightful presentation. I'm really interested in quantum computing, especially now that there's quantum artificial intelligence. So I'm doing a PhD in data science. My topic is about quantum computing and machine learning to improve the banking system, in the credit scoring processes. So maybe you can advise me how can I go about my research in terms of what I need to understand more, and how to combine the two together, machine learning and quantum computing, in order to improve the banking processes, like credit scoring processes. That's all, Professor. Thank you.
But maybe we can have that discussion separately. You have my email. It's my surname at san.ac.uk. You're welcome to send me an email and we can set up something. Yeah.
Thank you, Professor.
Yeah. And now I think it's time for Dean to take over. Dean, I think you already started sharing your screen. Please, you're most than welcome to start.
Thanks, Prof. And welcome everyone to the practical side of things. Yeah, from a very interesting talk now, we can see how to take those theoretical concepts and all the algorithms and gate-based things in quantum circuits, and it all seems very mathematical and very abstract, but how to actually implement that and really do quantum computing on real quantum computers and real computers in the first place. Most quantum computing actually happens through Python, which I'm hoping that most people are familiar with. It's quite an accessible language. There are all sorts of other implementations in different programming languages, but Python is where most people prefer to do it, which interfaces very well with other data science, machine learning, and other scientific programming packages. So the package that we'll be looking at specifically is one of the many offerings out there. There are very many simulators and software development kits and actual hardware interfaces offered by many different companies, very different individualized packages that are specialized for whatever different task. We will be using PennyLane, which is created by a company called Xanadu. They work a lot on quantum machine learning and quantum chemistry. They have their own photonic quantum computer. But PennyLane is the most preferable because it is a nice, neat, very Pythonic way of doing quantum computing. It's quite simple and easy to get started with, and it plugs into all other software development kits and quantum computing packages, and can plug into different hardware providers for real quantum computers without being stuck into a siloed system. It also connects very well with other data science machine learning packages like PyTorch, TensorFlow, JAX, anything you could want. So it's very versatile in what it can do. And we'll be using that mostly. It's very easy to get started with. Also, it's just a very basic pip install PennyLane. The website is also very good. I direct you to that. There are some links in here, but I can't share that directly now. But if you search for PennyLane Quantum, I'm sure you'll find it. They make it very easy to get started with their documentation, and they're very good demos. But for now, we'll basically just take what we've learned in the first part of the masterclass and apply it bit by bit here with some context. So if I repeat some ideas, then it's just for the context to remind you of what we saw in the first half of the talk. There are a few other packages installed here, but that's mostly just for the visualization that you'll see. You don't have to worry too much about them, but the basics are NumPy, Matplotlib, SciPy. PennyLane is the important one, and then another package called QTIP, which you'll see is just very useful for other quantum visualizations. It can do many other things, but that's for a whole other talk. Yeah, so for now, let's carry on. This is just the installation for it and some more important things, but we come to our first part of the building blocks, which is the idea of our qubit and what that means. And as we saw throughout the talk, the main use of this building block is just to encode whatever certain states into a quantum state. So yeah, we can have our ground state and our excited state scaled by some probability amplitudes of alpha and beta, and that can be represented by many different things, but for now, just to put the context, that's what we will be looking at. Now, when we look at how we want to actually implement these things, we look at our quantum circuits, and that's kind of the playground where we do things to our qubits. But for quantum circuits to actually make sense, it needs to be mapped to a specific device. Like, we want to know what are we going to be doing it on. It's to take it from this theoretical and abstract space where it's just this line on a sheet of paper, into turning into something that we can use. So for PennyLane, it's very important to how initialize or pick our device that we will be putting the circuit on. And for here, we keep the very basic one of just the QML, which is the typical default PennyLane import. Usually you import PennyLane as QML just because PennyLane is too long to type out, and QML referring to quantum machine learning because it was initially quite popular as a quantum machine learning library, but it's expanded much further than that. So whenever you see a QML, that's referring to PennyLane. their QML.device is where we can pick whichever device simulator we want. They've got many different options that they'll show in the documentation on their website. They've got many simulators, which make it very easy for us to use, where you can do the quantum computing directly on your laptop or in a Google Colab like this, where it simulates the states and does all the calculations in the background, including the things like the probability sampling, and you can include noise packages, which make it just a bit more realistic. You can do it on faster simulators. They've got a C++ backend, which just really speeds up a lot of the circuits. They have a GPU simulator if you want to use very big circuits, very big matrices. It also works very efficiently on GPUs. This is also where the plugin comes in for connecting to a real backend provider like IBM Quantum, where you can actually submit a job onto a queue to go into a real quantum computer that IBM hosts, so you can really run your circuits. So this device object here makes it very accessible to connect to whichever kind of simulator or hardware you'd like. When we pass this parameter of wires, that refers to how many qubits we're using, because when you look at the quantum circuit diagram, then it does look like just wires going across. So PennyLane refers to it as wires. When we define our device, then we say how many wires we want. So this is for a single qubit on their most basic state simulator, the default.qubit. Now that's defined, we can use this dev variable throughout the rest of our demonstration. And PennyLane offers a really nice way of wrapping our circuits to connect it to this device. The quantum circuits, how we use them in Python, is a very basic, as you'd expect, way of just defining any function that is your circuit. This will, in this case, return a QML.xp val of the QML Pauli Z, which is just the expectation value of the Pauli Z operator, which you'll see now is the most basic circuit that we could possibly think of. It doesn't really do anything, but it shows how to use a circuit. But what I really want to show here is this idea that PennyLane has called Q nodes, which is a very basic Python decorator here, or you can pass it through a function, but it's their way of making it very simple to package a quantum circuit in a very neat little box, where you can also then, you can reuse that in any other circuit call that you want to do, or you can, in bigger quantum circuits, you can have your smaller ones that you put into these Q nodes and then plug them directly in as a gate. So for example, returning to earlier, we had a question about if an oracle can be a gate. You can make your oracle circuit, whatever that may be, and then have it as this Q node, and then put that directly into another circuit as a gate. And PennyLane will kind of unpackage that in a nice form. So it's their functions of quantum circuits. For the circuit, what it actually does is really just initializes a qubit in the ground state and then takes a measurement straight away. It does nothing to the qubit, it just makes it and measures it. So obviously we'll get that we measure at the ground state, which is just an example here to say how we usually define and measure our circuits, which is in the most common and practical way of just taking the Z expectation value of our state, which is the measurement idea. There are many other kinds of measurements and many other kinds of samplings that you can take, or density matrices, or much bigger, more involved ways to see what your state is at the end of the circuit, but this is a very basic and typical one. As you see here, when we call the circuit in this form, it gives us an array of just 1, which refers to the Pauli Z expectation value of the ground state, which if you go through the maths, then you'll get 1. If you look for the excited state, then it'll be -1. Those are the two polarities of the two states. So with this answer not being really useful, it's just a dummy example that I can show you a few of PennyLane's functions with, where now we can just call a circuit and the expectation value, get an answer, but we can also then start to draw our circuits so we can actually see what we're doing. It's not just working in the space of getting numbers and using QML values, but we can actually see what our circuits are in a bigger sense. So it's got a very basic draw where it just prints it out. That's not really the most aesthetically pleasing, but it works, and it's the most basic example. We can use our matplotlib integration to actually draw the circuit. PennyLane also offers a few different styles or looks for how we want the circuits to look. They quite like a sketched look. You'll see in a lot of their diagrams, a lot of their figures, PennyLane quite regularly, even in some of their scientific papers, they use sketches for their diagrams. So they like to have this sketch version of their circuits that you can use just by setting the style to sketch when you call this draw matplotlib function. Another very good visualization, which is where the other package that I mentioned, Qtip, comes in, is to see what exactly does this qubit look like. because that might be a bit of an abstract question where you really want to get a physical grounding for what is the qubit actually, what is it? And you might have seen in a lot of other quantum computing things, and even earlier in this talk, when you look at this ball shape of it, where you compare your typical classical bit to just a 0 and 1 state, and then you have the expansion of a qubit into this whole sphere of possibilities and different ways that can be encoded in superpositions and all that. That comes through the block sphere. And the block sphere is that ball, which I mentioned, and it is a way of representing any normalized pure state, which is just fancy talk for just the most basic and general state of a combination of our ground state and excited state in terms of these two angles, theta and phi. These angles are important, as you'll see, because they define where exactly on the block sphere our block vector is pointing. The block vector being a summary of these angles, really. For QTIP, it's not really super necessary for this introduction. It might overcomplicate things, so feel free to ignore it, but in the documentation and examples explain it very well. This is just to show that here we can visualize our block sphere with the ground state qubit. Here with a nice block vector pointing straight up. This might seem a little bit counterintuitive, that you might think a ground state would probably be down and excited state be up, but this is just the way that it is. You'll get used to it the more you use this. So yeah, the very most basic representation of the qubit that we can do in its most basic ground state is just here, a sphere with the vector pointing directly up. This vector will usually almost always be normalized in most of the cases that you use. It can go through some noisy processes where it'll get smaller, but usually it'll just be the straight unit vector that points somewhere on the block sphere. And it is one of the best representation examples of a single qubit. Now, when we want to do something to our qubits, we think of quantum gates, which is then where the quantum goes through this process, goes along its journey towards the end of the circuit, going through these gates where things happen to it. Matrices act on it, different possible actions are taken on it. And returning just for context, we can talk about the X gate or the bit flip gate as the most kind of basic and primal example of what we can do to a qubit. So now I want to show what this looks like in all of its forms of what the quantum circuit looks like. Instead of just having our circuit then straight to a measurement, we put in here one line of QML.x for the X gate acting on our first qubit, or with Python indexing the 0th qubit, because there is only one. But with bigger circuits, then you can choose which qubits it acts on. So yeah, it's very basic of just, like I said, straightforward of you put all the gates that you want in the order acting on the qubits that you want, and then that's all it really takes. So it really simplifies the idea of quantum computing, that you have to code this massive thing into just a single line for a single gate. Very basic circuit. And we see when we do a bit flip or X gate onto our ground state, it'll give us the 1 state, or our excited state, which, like I said earlier, for the Pauli expectation value, the Z expectation value, it goes between in polarities. You get 1 for your ground state and -1 for your excited state. And then naturally, that's exactly what we get out of the circuit. And again, we can draw the circuits to make it a bit more visual and see what we're doing. Again, passing just through this exact circuit that we've measured here, or that we've constructed. And again, on the block sphere, a bit more complicated, but to show what it does, that it takes it from the ground state and it rotates it around the x-axis there to the excited state as a direct bit flip. Now, starting to get a bit more clear what the visualizations are and what's going on when we're acting on this qubit. And hopefully it's setting in a bit more about how we can really practically do all of these things. There are many other gates, as we mentioned earlier in the talk, of
So it seems we have lost the speaker. Let's see if we can get him back online quickly. Just a minute of patience to allow the speaker to come back. Here he comes.
Sorry about that.
Okay, you're back.
Yeah, hopefully I didn't lose too much time or talk too much while I wasn't presenting. But returning, I hope we were here, where I was talking about the different gates that we can apply, and returning to just the different examples and how we can enact that on a quantum computer, specifically in penny lane. And now when we return to different gates of, for example, a RX gate, which is a bit more involved one because it actually takes a parameter. It's not just a bit flip or a phase flip like the basic Y and Z. But if we look here at the rotation gates by RX by this angle theta, what we do is to not do a full just bit flip, but we can control different angles of where exactly we put this block vector and how we can act on a qubit in a more fine-tuned and parameterized way. And that's defined just for in the RX example. There are obviously the RX, RY, and RZ for the different rotations that you can do, and many others. But for the RX gate by an angle theta, it's defined by this matrix, which will then act on whichever state it's applied to. Now we can look at an example of, instead of a full 180-degree or full pi rotation, we can look at just a halfway for a 90-degree or pi by 2 rotation around the x-axis. Where for now, when we create this circuit, we have to define it by this parameter of theta. And this, where before we do QML.x and just put 0, that parameter is, is actually referring to this y is equals 0. And this is, I make a point of this to not get confused between when we initialize the device, we say the device, the qubits, and that y is equals 1. But that is defining how many y's we have or how many qubits we have in the circuit. But here, when we talk about y is equals 0, that's talking about which y or which qubit we are applying this to. Because for other kinds of gates, y is plural is because you can apply it to many qubits at once. But that's a topic for another day. But just make a point of this to not get confused between where we say y is equals 0 or 1. And a different measurement that we were doing here, just to have a bit of a better look, to not just collapse the state into a value z expectation value and get a not full answer, we are going to look at the density matrix, which is a full look at exactly what's going on inside of the qubit for all of its different values inside the matrix of the state. And here we can see a bunch of our 50-50 states, even here with the off diagonals and imaginary states. We'll see a bit more what that means when we look at the block sphere representation. Again, we can just look at the circuit representation here, where it's important when you pass the circuit, we also have to pass a parameter of what the circuit takes, because the circuit does take a parameter. It's not just empty. Even though it doesn't represent the pi by 2, but you can look deeper into documentation to see what exactly you can do with these circuit representations. So now returning to the block sphere representation, we can see that our pi by 2 rotation, instead of the bit flip rotation, only does halfway to this point here. Where if we were to take a z expectation value measurement of this, then it would essentially just collapse that block sphere state, and then we'd get the 50-50 state. But then you'd lose the other information that you have, which is why I wanted to show the density matrix, that there is more going on here than might be seen with just the z expectation measurement. There are many other gates that we can look at, for example, like this P gate, which changes the phase, but that's not the most interesting to look at. Based on what we've seen now, the much more interesting one to look at is the Hadamard gate, which, as we mentioned in the talk earlier, is a very, very important gate because it is used specifically to create an equal superposition of two states, as can be seen here by acting the Hadamard on the ground state. It gives you the state where you can use for your random number generator or your 50-50 coin flip, quantum coin flip example. And for now, I just want to show the visualization of what that is, because here it's important to note that it's not just a RY gate that rotates it by pi by 2 to get it down across onto this point, but it's a rotation around the XZ axis, which takes it around this curve here to get to the superposition state, which is important because if you do just 2 RY rotations by pi by 2, then you'll get to the other side. You'll just get to the excited state. But if you do 2 of the 2 Hadamard gates, then you'll get back to the ground state, which is what makes it emission, or it's what makes it its own complex conjugate. It's a very useful gate, and that makes it very useful in all its little mathematical tricks that you do with it. But to show this visualization, which I know I looked for a long time when I was trying to make sense of quantum computing back when I first started. So now that we have a lot of our gates, we can start looking at putting them together for an algorithm. An algorithm that I want to show here in this implementation is a simple variational circuit on a single qubit. So thanks to the very good introduction earlier, the talk about what a simple variational circuit is, it probably shouldn't be too strange of a jump now, but it's essentially, it's a very useful algorithm that can be done in very basic format with a single qubit that spreads into other parts of quantum computing in very useful ways. Like this is the basis for a lot of quantum chemistry, for quantum optimization, for quantum machine learning. It spreads really, really fast. So it's a very good basic example to learn, because once you know kind of fundamentally how it works, then it's very easy to adapt into bigger settings. So a variational circuit is also very useful for modern quantum computers, where it's the NISQ or NISQ era, where it's still a bit noisy and it still needs a bit of help here and there from, you can't do everything on the quantum computer. There's some things that it's really good at, but there's some things that it's much slower than regular computers at. So it shares this hybrid field where you can do the fast things for quantum on a quantum computer and the fast things for classical on the classical side, where you can pass back and forth and share the responsibility to make the overall algorithm very fast and efficient. This variational circuit that we want to show here is a basic setup just using 2 rotational gates, which is how we encode the information into a qubit. Because that's also a good conceptual thing to note, that with a classical computer, when you want to put whatever data into your algorithm that you then want to vary and move around and change and tweak, turn the dials and optimize, it's a very weird series of encoding hierarchical balances of your 0 and 1 bits into these different gate setups, logic gates, and into much bigger algorithms. That's why you get bytes and kilobytes, and it gets very complicated. But for a quantum computer, you can encode these angles directly onto a single qubit, just with these rotations. And then that holds the information in the qubit for you to then act on and then measure on and tweak. So it keeps it very nice and localized in one place, which makes it also very efficient. It's quite an elegant comparison to how we do optimization or machine learning on a classical computer. So this variational circuit encodes these 2 very basic angles of very basic gates, just as our example that we want to work with here. So once we have these rotations, now we want to look at what's the cost function, because we want, when we vary something, when we're using variational circuits, we want to take it from some point and then vary the parameters and tweaks and dials to get it to another state, to improve upon that solution iteratively. The cost function that we're using in this setting is just the Pauli Z operator. This is a very basic example. It's not going to be or quantum GPT or encoding a full MNIST dataset for handwritten digit image recognition, but it is going to show the basic ideas behind it. But for this stage, we're using 2 very basic rotation gates and the Pauli Z expectation operator as our cost function. And that'll make a bit more sense as we go through, but it is quite a simple circuit with a simple goal. But essentially the goal for all of this is to tweak these 2 dials of these 2 parameters of our theta 1 and theta 2 or theta and phi, until we can get that cost function minimized or maximized, depending on how you want to approach it, but just optimized. So let's get more into the implementation where we can see what exactly is going on here. Also important to note here, for when you do start working with PennyLane, that PennyLane has its own subversion of NumPy that makes it work nicer with its own functions, which is just a bit of a quirk of PennyLane, but important to know because that can cause a lot of issues if you're just using regular NumPy. But yeah, so keep in mind of this. And when we initialize our device now, it's also important to know that there are more features that we can use with the device. And one that I want to demonstrate here is this shots argument. And shots is essentially how many times we sample the quantum state and take these measurements, because as we mentioned throughout the talk, it is all probabilistic. From just one measurement, you won't exactly have the full answer. Like if you have your random number generator or your 50-50 quantum coin flip, you won't always get exactly the answer that you expect. But if you do it many times, almost infinitely many times, then it will converge towards that 50-50 split. For when we don't define the shots, then PennyLane defaults to just doing the exact calculation of what it will end up as. But here we can subsample what's going on, because when you apply this onto an actual quantum computer, every time you're going to have to tell it how many times to do that measurement, to run that circuit, to get an answer, and then take the probability distribution over all of that. So here we can kind of artificially, through the simulator, define these shots and define how many times we want to measure the circuits to then get a probabilistic answer. Here, 100 shots is around a good balance. It's fast enough, and it will still give us the probabilistic behavior we're looking for. You know, typically use on the scale of a few thousand to get more and more accurate. You can also set it to shots equals none if you really want the exact solution, just to show the diversity that PennyLane has in ways to use it. So again, now with our device defined for our default qubit, for a single qubit, and for 100 shots, we can again define it as our Q node in our circuit of our Rx gate for a parameter, where this parameter argument that we pass is a vector of two values for your first parameter and your second parameter. This will be your Rx and your Ry, and then we take our expectation value again. Now, for a basic example of how this will run, we set up a NumPy array of our vector of parameters. We pass that parameter to our circuit, and it'll give us an expectation value. To draw the circuit again with our same parameters from earlier, we can then see that this is starting to look like the example circuit we're trying to replicate. Now, this circuit returning to this cost function we were talking about, it will really just give the state defined by these angles, where when we look at our cost function, we're going to pass it the same circuit that we define now, which is not typically how you do it. Usually it'll be a mean squared error or something, but that's where you have specifically data that's labeled and you're passing in, and you can compare it to something and then see how far away your current answer is to the ideal answer, and that's your cost or your loss function that you then want to optimize. But for yeah, we can just pass the circuit because we are trying to find a specific state within the circuit that is defined by it. Specifically in this, we are looking for the excited state. So we are taking it from the ground state initialization. We are applying two rotation gates defined by these angles. Essentially, it's to just find the excited state. So it's just looking for where it can do a bit flip. Which is why I say it's not the most practical example, but it does show the working principle for everything. So right at the end of everything, when we start this expectation value, we want to be -1 because that is the Pauli Z expectation value of the excited state. We're going to tweak and train these parameters in a variational loop until we find that answer. And how we do this is through this variational loop is quite reminiscent to if you've done work in data science, machine learning, or AI before, where we work through optimizer. And the most basic example of that is your gradient descent optimizer, which just uses the basic calculus to then get to minimize that loss or optimize that loss. There are many other optimizers that we can use, the more popular ones for machine learning, like Adam optimizer or Adagrad or whichever kind you would like. Penny Lane has most of these built in because it was for quantum machine learning initially, and it's since evolved, so it has even more. But in a very basic sense, we can just initialize our optimizer here as QML.gradient descent optimizer with whatever step size. Again, very basic, just with QML dot. It can do many, many things. You can find all the other optimizers that you'd like here in the Penny Lane documentation and fiddle around and see which ones work best for what. We initialize how many steps we wanted to take for how many iterations we want this optimization to go through, and we initialize our array with the first parameters that we want to try. Usually this can be just a random initialization, but just for example, I'm keeping it the same as what I used in the single sample earlier. And you might notice that this number is a bit different because it's probabilistic, so it won't be exactly the same as before because it's taking random shots and getting a bit of a rough distribution of it, as you would expect from a real quantum computer. Now, when we run this loop, we can keep track of the previous steps of our loss to see if we are improving or not. We run it through a basic for loop, how many steps we have. When we pass it through our optimizer, we want to get our new parameters as an output of the optimizer taking a step along from our cost function, which is our quantum circuit, and the parameters that we'd had in previous step, and seeing how do these parameters work, how far away is that from the ideal solution looking at the cost, and then how do we step it one little bit closer along the gradient descent towards our new better parameters. And I'll just print along how we go, and then we can see through this loop, it starts out with not a very good state. That's not the ground state, the excited state we're looking for, but bit by bit it gets there. And when we want to plot this, we can see that it janks around a little bit when it tries to find its way, and then but it does follow a good slope towards the correct loss function, and it then converges around 70 iterations. And when we find the optimal set of parameters, we do find that it's exactly the excited state that we were looking for. So in the most basic sense, we have now completed the variational circuit loop, and it's 2 or 3 steps away, and then you do full-on quantum machine learning or quantum chemistry, quantum optimization. This spreads into all sorts of things that now you should be able to do with Penny. As most basic example, you extend it to a few more qubits, so you extend it with a few more parameters. You can encode the data and then run the same circuit. And this is how most of quantum machine learning is done. Yeah, so I hope that this has been a very nice example to see that you can take from what you've just learned about all the mathematics and all of the circuit representation, all these abstract ideas, and really put tire to tar, so to speak, of actually encoding the stuff and using Python to create a quantum computing algorithm. And from here, it's also a step away to running it on a real quantum computer. And then that kind of shortens the distance between you and quantum computing. You can do it on your laptop at home or from a web browser using Google Colab. You can really do full-on quantum computing. Yeah, with that, I'd like to hand over back to Prof. Francesco to go from there.
Yeah, thank you very much. Okay. Thank you very much, Dean. Sorry, we had a little bit of echo issue. Yeah. Are there any questions for Dean? I think we answered a few online.
Maybe turn up your volume.
Yeah. Then should I use this one here? Which volume do you want to use?
Use your volume if you want to talk that easy.
Okay. Perfect. Okay. Yeah. So there's a question by Pumzile. So are annealing architecture more costly to use versus gate-based architecture? I think the answer is probably no. I think the annealing architectures are usually, I mean, it depends what you do, but usually I think they're more affordable. Yeah.
They're also very curated problems.
Yes, they don't solve universal problem. They solve specific classes of optimization problems. Yeah. And a few people ask for a certificate. Yeah. If people desperately need one, we would be very happy to organize one. No problem. Yeah. Do we have any raised? Should I give let me give you the permission to speak.
Yeah.
Hi, Daniel.
Hello. Hi, yes. Thank you very much for the two talks. I must say I felt very small in the first talk, like I was listening to Einstein. I'm a software developer, and then when Dean came on, it was more my medium. I thought, yes, Python, maybe I can get a grasp of this. My question is, Penny Lane is a simulator on a classical server, I imagine. How is it mimicking quantum? That's the mystery to me.
No, you can use Penny Lane and run the code on a quantum machine. Yeah.
Okay. But where can I get my hands on? Where can I buy one?
Yeah.
Or is it too soon?
If you can buy one, you will be my best friend.
Okay.
No, but there are some quantum computers in the cloud, and some are also freely available for a small number of qubits. Yeah? There is, for instance, the IBM cloud, Amazon cloud, Microsoft cloud. They all have quantum computers available for.
Okay. But is Dean saying that if I build up, somehow get up to speed using Penny Lane and some examples, when someone gives me a check or hands me access to such things, I will be at least walking instead of dead still.
Just change a line in your an option in your Python code when you choose the device. Yeah.
Okay, thank you.
You will have then to upload your API code or whatever, and then off you go. Yeah. But the code remains the same. Yeah.
Thank you.
Are there other questions, comments, you guys? Yeah. Yeah, please ask.
In category theory, to take topics.
Yes.
Then the products model the AND gate.
Yes.
And like exponentials model implication and so on. Do you know if someone has studied the same for quantum gates?
Yes, that's what Kishan will do this afternoon.
Okay.
That's exactly this afternoon. Yeah, so just as an advert, this afternoon we have a mini school on ZX calculus, which may be another approach to quantum computing. Yeah, and that's why we asked Kishan to do it. Yeah, because that's interesting to many people. Yeah. Okay, if there are no more urgent questions, then thank you very much to all the participants at various venues. Yeah, and we will soon announce another masterclass next month, and maybe in a couple of months we will do another one on quantum computing to make sure that we do also the more fancy thing. Yeah. So Dean, thank you very much to you for your presentation as well. Donovan, thank you for organizing the back end. Yeah, and thank you to all participants, and we will see you soon. Thank you very much. All the best.